Hello everyone, welcome to another physical science lesson. Today we're going to be continuing our investigation on electromagnetism, and in particular we're going to be looking at something very interesting. We're going to be looking at the magnetic field that you find around a loop or a coil. So let's go and have a look at what we're going to be discussing today. So if you look here, magnetic field around a loop or around loops and coils, I wonder what that might be about. And so as we look over here, we're particularly looking about an electric current that passes through a loop. We're looking at an electric current that passes through a loop. So the current passes through the loop, and we want to say, well, what's the magnetic field going to look like if it's passing through a loop? And later we'll look at a coil and say, what's the magnetic field that is around a coil? Right. Now, have you ever thought about what might change the pattern of the magnetic field around a conductor? And how could we change it? Maybe there'd be a different sort of pattern shape around a loop or a coil, and that's what we're going to investigate. But is there another way of thinking about changing this pattern that we get around a conductor? Well, you think about it and maybe we'll answer it as we go along. So the question that I want you to think about is, how can you change the magnetic field around a conductor? Different ways of changing it. So we want to just quickly revise some terminology that is common in this section, namely the right-hand rule. I hope you can remember what that is. Remember, you take your right hand and you're going to show the direction of the current using your thumb. So if the current is passing up, then you point the thumb up. If the current is down, you point the thumb down. And then what do you do with the fingers? The fingers give you the curl of the direction of that circular pattern around a straight conductor. We're going to use that and see what happens when we do it on a coil too, or on a loop. We're going to talk a little bit about the magnetic field strength. How do you know the difference between a strong field, or region where the field is strong, and the region where it's weak? How can we represent that? And here's a new term, magnetic flux. Let's have a look at each of those terms. So I want to start off by just revising the use of the right-hand rule. We're going to do this quite quickly, but we must make sure that we understand it. So let's go and look at that experiment that we've done before, simulation of the experiment at least. We're going to look at the field pattern and the direction of the field when we current passes through a conductor. And so let me have a look at this particular simulation. And here we go. Now you'll remember that we can see these iron filings. They're kind of in a pattern, but it's not a very convincing pattern. But there's an opportunity here to change the intensity of the current, to change the strength of the current. And if you look at that pattern, it's even more scrambled. So if we increase the current, look what happens. It becomes more defined. And if we increase it a little bit more, it jumps and it forms this nice circular pattern. So clearly by increasing the current, we can change the pattern. But one of the other things we could do is we could change the direction of the current. Now the pattern doesn't change, but what does change? Have a careful look. Look, the direction that the compass needle was pointing in changes. And I want to just make sure we've got that in terms of using the right-hand rule. So when the direction of the current over here is going from positive to negative, and we recognize then the current is going down, can you see that the thumb points down and the curl of the fingers is in that clockwise direction? Whereas if I change the direction of the current, it's now going up and the direction of the field is in the opposite direction. So we need to recognize that changing the current strength changes the direction, changes the intensity of the field pattern, changing the direction of the current changes the direction of the magnetic field. But what's important here is that in both these cases, the magnetic field is still perpendicular to the direction that the current is passing through that conducting wire. And so you recognize they're perpendicular to each other. Now, if we go to the next slide, we recognize that we've said the magnetic field, the strength of that magnetic field is called magnetic field strength. It has a symbol B, which is measured in Tesla. We're not going to do too many calculations with this. It's just a measurement of the strength. And we recognized when the pattern, when those iron filings are closer together and they're all clustered together, that means the field is stronger. And we're going to be looking at that in a little bit more detail. Now, if we were to represent this magnetic field around a straight conductor, we use dots and crosses, and we use this notation, again, just showing the right-hand rule. If you take a look, you'll recognize the direction that the current is going is from positive to negative. So the thumb points in that direction. And look at my fingers. They're going into the board over here. That's why there are crosses there. Whereas on this side, as I'm pointing in that direction, can you see my fingers are coming out of the board? And the dots indicate the direction of that field. The dots are saying to me the current is coming out. So it's that circular pattern that we've seen before in terms of where the magnetic field is. So if we wanted to recognize the strength of the magnetic field, where is it stronger? Well, where the dots are closer together. And I've drawn a little area, a little square, to say this magnetic field is passing through an area that I selected. And there are lots of field lines that are parallel to each other that are passing through this area. So they're kind of clustered together. There are lots of them per unit area. It's kind of like a density idea. The more there are in a certain space, but it's not density, because density would be mass over volume. This is the field strength divided by area, and that area is at 90 degrees to the field lines that are coming through there. So we'd recognize when they're close together, there is a strong magnetic flux. There are lots of field lines in a small area. And that's a new term. It's a relationship between field and area. Now look at the same area over here, and you'll see the square that we're using is exactly the same size and shape, but we've got far fewer field lines passing through it. So the magnetic flux is weaker. The important thing about magnetic flux is not only that it's the field strength times an area or per unit area, but we're recognizing that it is that area is at 90 degrees to the field lines. So let's formally define magnetic flux. So magnetic flux has an interesting symbol. It's this strange looking Greek letter, which is called phi. You might have heard of pi. This is phi. Quite similar, but just a different shape. And you need to be able to recognize how to draw it and to make it clear. Now, the formal definition, or the equation that we use to define magnetic flux, tells us that it's the product of the magnetic field strength and that area. Remember, that area that is at a normal, or in other words, normal to B. In other words, at perpendicular to B. Now, this angle here causes people some confusion. If for some reason you have a strange magnetic field that might not exactly be passing through an area at 90 degrees. Say we examine a situation where the field lines are passing through at an angle. They're not at 90 degrees. Then we will have to take a look at making it the difference in the angle between the normal and the area. So this angle theta is the angle between the normal and the area. So theta stands for the angle between the area and the normal. So it's a component, if you like, of the area that needs to be at 90 degrees. Because at 90 degrees, that's where it's going to be the most effective. It's the best way to compare what the actual flux is. Because if it's just hitting a little bit, well, we'd not get a good idea if the area wasn't exactly right. So the unit here is called a Weber, and the symbol is WB. Right, guys, that's the beginning of our little introduction to what happens when we look at loops and coils. Take a short break. We'll be back after this.